Okay, good morning, everyone. So last time we had been talking about addition of angular momentum. And so the idea is we have two generic angular momentum operators. And so the first thing we want to consider is what's a complete set of commuting observables for these operators? And there are two good answers. One I'll call complete set of commuting observables number one, and that consists of J1 squared, J2 squared, J1z, and J2z. And so this just is sort of taking the complete set of commuting observables for J1 and the complete set of commuting observables for J2, and that's these things and those things, and then just putting them all together. And so we called that the product basis CSCO. Because they commute, we know that we can find a basis of elements that are common eigenstates of those. And we write those as M1, M2. And the idea is we don't have to write J1 and J2 because that's going to be the same for any CSCO. So for example, a complete set of commuting observables number two is J1 squared, J2 squared, but instead now we take J squared, the operator for the total angular momentum squared, and J sub z. And this is called the total angular momentum eigenbasis. I'll just write basis here. Okay, and we label those by M1, or sorry, J and M. And then on rare occasions, we might get confused because each basis set is labeled by two numbers. So I'll use a comma for J and M and a colon for M1 and M2 whenever there's a chance of confusion. So one case where there wouldn't be a chance of confusion is if I'm writing symbols like J and M or M1 and M2, but if I'm just writing numbers and the first number is positive, right, then it could be J or it could be M1, and so that's why the colon is used to distinguish them. Okay, so in different circumstances, and we'll talk about which circumstances are which, you might want one basis or the other, and so we want each state Jm to be a sum of M1, M2 states, and we want to know what the sum is. So one thing we can do is write it as a sum over all M1, a sum over all M2 of the allowed values, times the product basis state, M1, M2, and then the coefficients that go here, according to completeness, are some matrix elements. Okay, and so what we need are these matrix elements. And those are called Clebsch-Gordan coefficients. Okay, so that's the general task. And so we're going to start with the example of two spin 1/2 states, or two spin 1/2 operators. So we'll call them S1 and S2. And so the first thing we want to do is write down the product basis. The states in the product basis are just going, there are four of them, and they're going to be the following. There's up arrow, and up arrow, and down arrow, up arrow, and down arrow, And the first of the labels in each case is the S1Z eigenvalue label. So if it's up arrow, that means it's h bar over 2. And the second label in each case means the S2Z eigenvalue label. In this case, it's also h bar over 2 because it's pointing up. Okay, so now the thing we need to do is to ask, how do the total spin operators act on these states? So the total spin operators are s squared and s sub z. That's the second CSCO. How do they act on these states? And then once we know that, we can figure out what are their eigenstates in the product basis. And that will be the answer to the question of addition of angular momentum. Okay, so it's a good idea to start with S sub z first, because we notice, and this is actually a general feature, that the eigenstates of S1z and S2z are automatically eigenstates of SZ total. So we automatically have the eigenstates of S sub z, because S sub z is just S1z plus S2z. Okay, and to enumerate them, let's let epsilon 1 be plus or minus a half, and epsilon 2 be plus or minus a half. Those are just the possible eigenvalues of S1z and S2z. Okay, and then if we act with S sub z total on a state epsilon 1, epsilon 2, those are really the up arrow, down arrow states in a different notation. This is S1z, epsilon 1, epsilon 2, plus S2z, epsilon 1, epsilon 2. And now we can evaluate these by just looking at the first label for S1z. That makes this h bar epsilon 1. And this one, the second term, we evaluate by looking at how it acts on the second label. So that's it, h bar epsilon 2. And so the total thing is just a number, namely h bar times epsilon 1 plus epsilon 2 times the state back again. Okay, so that means that's the eigenvalue equation. And so we can just plug in the different epsilon 1s and epsilon 2s to get that S sub z acting on the state up arrow is h bar times the same state back again. Okay, and S sub z acting on the state up arrow, down arrow, that gives 0 because the up arrow and the down arrow cancel in the eigenvalue. Same thing for SZ down arrow, up arrow. Those both give 0. Okay, and S sub z acting on down arrow, then is going to be minus h bar, down arrow, down arrow. And so all of this tells us is that we have the representation of the operator S sub z in this basis of 4 states. It's a 4 by 4 matrix. I can pull out an h bar, and then it's just 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, minus 1. Okay, on the product basis.
I'm sorry, Professor, why was that one 0?
Sorry?
Sub z on the up and down. Why was that one 0?
You mean here?
Yeah, and the next one, yeah.
Right, so this one has epsilon 1 equals 1/2. And this one has epsilon 2 equals what is minus 1/2. Okay, and then we're adding them together. Okay, and the same thing here. So we're just adding together the different z component eigenvalues, which happen to be pointing in opposite directions. Okay?
Oh, since we're adding them, it would be 0, correct?
Right, we are adding them. Okay? All right. So this is on the product basis where, for example, 1, 0, 0, 0 is representing up arrow, up arrow. So when I wrote this matrix, I was using the ordering of states exactly as up here. Okay, those are the 4 states in order. All right, good. So we have S sub z, and now we can ask about what about S squared? So what about?
So professor, that up arrow, down arrow wouldn't be 1, 0, 0, 1 vector?
Up arrow, down arrow.
Yeah.
So are you asking in this basis up arrow, down arrow? So this is the second thing in the, it's the second basis vector. So its representation is 0, 1, 0, 0.
Oh, so you're saying that SZ acting on that is 0. Is that what you're saying?
SZ acting on that is 0. Right. That's what this says. Okay. All right. Let me erase this. Okay, so what about the total S squared operator? So this we can write as S1 plus S2 dotted into S1 plus S2. That's its definition. Okay, and so we can write that out. S squared is, there's an S1 squared term and an S2 squared term. And then there's the cross terms, 2S1 dot S2. Okay, and S1 squared is a fixed number. It's 3/4 h bar squared because it's S times S plus 1 times h bar squared. S2 squared is also a fixed number. Okay, and then S1 dot S2, one can look back in the note. Well, one way to do it, let's just do it completely. So this is 2 times S1x, S2x plus S1y, S2y plus S1z, S2z. That's the dot product written completely out. Okay, and now we can figure out how to write this a little nicer by doing the following. If we take S1 plus is S1x plus I S1y, and S2 minus is S2x minus I S2y. Okay, and we multiply those together, we will get S1 plus S2 minus equals S1x S2x plus S1y S2y plus I times S1y S2x minus S1x S2y. So that's kind of a mess, but now if we do the same thing, but with pluses replaced by minuses everywhere, then what's going to happen is we'll get the same 2 first terms, and the plus and minus just changes the signs in front of the I terms. So this will give minus I times the same thing. And so what that's telling us is when we add those 2 things together, we get something nice. namely S1 plus S2 minus plus S1 minus S2 plus, is exactly what we want in the S squared equation, namely this. Okay, so now we can take this combination right here and replace it by that. That's going to be a good idea because the plus and minus spin operators act nicely on product eigenbasis states. And then what's left over is the z component ones, but the z component ones are simple because we're using eigenstates of S1z and S2z. Okay, so summarizing all of that, S squared is 3/2 h bar squared plus S1 plus S2 minus plus S1 minus S2 plus 2 S1z S2z. So the idea behind all of this is to get things in a form where we can act easily on product eigenbasis states. And so the claim is that that way of writing S squared has accomplished the task. So recall S plus, and I'm not putting a label on it because now I'm just going to do this generically for any single spin. S plus acting on up arrow is just 0. That's saying if it's already pointing up and you try to increase the eigenvalue, it can't be done, so it gives 0. But if I raise the lowered spin state, I get h bar times the raised spin state. If I lower the raised spin state, I get h bar times the lowered spin state. And again, if I take a lowered spin state, a state with spin pointing down, and I try to lower it further, I can't do it, so I get 0. Okay, so those are the things that we're going to use when we apply these operators right here. So let's go ahead and do that for each of our basis states in the product basis. So S squared acting on up arrow is going to have the following terms. There's going to be the 3/2 h bar squared times the same thing back again. Okay, and then for the terms with S1 plus and S2 plus, those are both going to give 0 because in both cases we're trying to raise a spin that's already pointing up. So those terms both give 0. And then finally we have this last term, which is going to give 2 times h bar over 2 twice, one for S1z and the other for S2z, acting on the state up arrow. And so that's 3/2 plus 1/2 times h bar squared, which is 2 h bar squared up arrow. So what we found is the up arrow state is actually an eigenstate of S squared. Okay, and then you can do the same exact thing for the down arrow, and exactly the same way it turns out to be 2 h bar squared times down arrow. So that's also an eigenstate. And we have 2 more to go. So we have S squared up arrow, down arrow. So again, there's the term 3/2 h bar squared times the identity. Okay, the next term, if we go up here, there's a term here where we're trying to raise spin 1, which is already up. So that's going to give 0. Okay, so this term we don't have to worry about. This term right here, we're lowering the first spin and we're raising the second spin, so that actually works. And so that gives plus h bar times h bar. here we're using this equation and this equation. Okay, multiplied by down arrow, up arrow. And then finally, we have the last term here in s squared, which is going to give 2 h bar over 2 for the up arrow minus h bar over 2 for the down arrow times the same state back again. Okay, and then when we add that up, this gives h bar squared up arrow down arrow plus h bar squared down arrow up arrow. Okay, and then finally, s squared acting on down arrow up arrow, that works exactly the same way and it gives exactly the same answer. Okay, so I'll just write here same way. Okay, so now we've figured out how s squared acts on each of the product basis eigenstates. And so the result is the representation of s squared in this basis is h bar squared times 2. That's for the first one, and there's all zeros. And then there's 1, 1, 1, 1 for the up arrow, down arrow states. And then there was a 2 here also for the down arrow state. So that's the 4x4 matrix. And fortunately, there's enough zeros to make calculating the eigenvalues and eigenvectors very easy. So the eigenvalues are 2h bar squared, 2h bar squared, 2h bar squared, and 0. Okay, and we recognize that this is going to have eigenvalues that are the possible values of s squared. And so this is total spin s equals 1 because s squared is h bar squared s times s plus 1. Okay, and this is total spin s equals 0. Okay, and then the corresponding eigenvectors for these are, for the s equals 1 eigenvalue, we already found that they were, oops, that's not right. They were up arrow, and down arrow were 2 of them. And then the one that comes from looking at this part turns out to be just 1 over root 2, up arrow, down arrow, plus down arrow, up arrow. Okay, and then for s equals 0, there's only one state because there's a non-degenerate eigenvalue. And normalizing it, that's going to give 1 over root 2 up arrow, down arrow, minus down arrow, up arrow. Okay, and as a check, all these states are orthogonal to each other. They form an ortho basis. In particular, when you take the inner product of that one with this one, it has to give 0, and it does. Okay, so we're basically done with the addition of 2 spin 1/2 angular momenta. If we combine the information from s squared that we just calculated and sz, then I can write a column here, which is the total spin basis with eigenvalues s and m. And in this column, I can write the product basis with eigenvalues m1 and m2. Okay, and so here we had states that we can label 1, 1. That was equal to up arrow. We have 1 minus 1, which was down arrow, down arrow. And the reason we know those are because we know what S sub z was for both cases. We're defining S sub z to be the second entry here. And then we calculated it to be plus h bar for these and minus h bar for these. Okay, and then we have in this column 1, 0, which is 1 over root 2 times the sum of these states. Okay, and so these form a triplet. And then finally, we have the 0, 0 state, which we write as 1 over root 2 up arrow, down arrow, minus down arrow, up arrow. Oops. Okay, and so that's the singlet state, the spin 0, total spin 0 state is the difference. Okay, so we've accomplished the addition of angular momentum problem. We have written the total spin basis states as linear combinations of the product basis states. And it turns out that really it's a trivial linear combination except for these two. Okay, so one way of writing what one has accomplished is one writes that if you take 1/2 product 1/2, you get the direct sum of spin 1 and spin 0. Okay, so one says direct product of angular momentum more generally than spin. Because once you've done this for one angular momentum, it's good for any angular momentum, no matter what physical role it might play. It might be spin, it might be some other kind of angular momentum where you take a linear combination of other spins or something like that. But in any case, that gives the direct sum of angular momenta 0 and 1. Okay, so a very useful thing to also notice from what we've done here is what happens if we interchange the two spins. So if we interchange a spin up and a spin up, nothing happens. If we interchange a spin down and a spin down, nothing happens. If we interchange these two spins, then that turns this term into that term. And if we interchange these two spins, it turns that term into that term. And so again, the state for each of the triplets is unchanged if you interchange the two spins. But for the singlet state, this state turns into that state where it acquires a minus sign. And this state with a minus sign turns back into that state. And so we can summarize this by saying the triplet states in this problem are symmetric under the interchange of spins. And the singlet states are antisymmetric. And this is going to be very important when we start talking about identical particles. Okay. So before we go on to start doing more examples, let's answer the question of which basis should we want to use? And unfortunately, I can't give you a completely foolproof answer to this question, but I can give you some indication. And so it's a general principle in quantum mechanics that if at all possible, you want all your important operators to be diagonal, if you can. Now, sometimes you can't accomplish that, but usually the most important operator is the Hamiltonian. And so you want, if you can possibly do it, you want the Hamiltonian to be diagonal. Sometimes it's too hard to see how to do that right away, but that's often the goal. So suppose your Hamiltonian has a term that's important that looks like the following. Something like a constant, I'm putting a minus sign in front of it because that's what usually happens, times a spin dotted into a magnetic field, and another constant times another spin dotted into a magnetic field. Okay, and so by the magnetic field, so spins correspond to magnetic moments of particles. Magnetic moments, their contribution to the energy is the dot product with the external magnetic field. And so here the B is some external magnetic field, which is pointing in some direction. Okay, and A1 and A2 are constants. They might possibly be the same constant. They might be different constants. Okay, but if this thing is pointing in the z-hat direction, and we might as well choose our coordinate systems to make it point in the z-hat direction, then this is going to be minus A1 times the magnitude of B times S1z minus A2, whatever that constant is, times the magnitude of B times S2z. Okay, so this is going to be diagonal in the product basis. So if you see a term like that, that's a signal that you probably want to be using the product basis. The product basis is eigenstates, by definition, of S1z and S2z. And so if you're in such eigenstates, these terms will be automatically diagonal in that basis. Okay, and so for example, if they're spins like this, then the basis will be the one we wrote down at the beginning. So up arrow, down arrow, up arrow, etc. Okay, on the other hand, that's one thing that happens a lot. Another thing that will happen is suppose that the Hamiltonian is the dot product of two spins with each other rather than with an external magnetic field. And there's a standard trick. And in fact, I would go so far as to say, if you're taking a PhD candidacy exam or doing a homework problem, and you see a dot product of two angular momenta, the chances are very high that you'll want to use the following standard trick. And that is you write it in the following way. So this applies even if they're not angular momenta. You write this as 1/2 the dot product of the total angular momenta into each other minus S1 squared minus S2 squared. So that's 1/2 S squared minus S1 squared minus S2 squared. Okay, and the nice thing about that is that's diagonal in the total angular momentum basis. Okay, or in this case, if they're spins, this is diagonal in the total spin basis. Okay, where the eigenstates are labeled by S and M. Or maybe I should call it M sub S, just to be clear about which M it is. Okay, now the tricky part is, what if your Hamiltonian has both types of terms, like that and like this, and then neither basis is going to be perfect. Whichever basis you pick, one of the Hamiltonian parts will be diagonal, maybe that one, and maybe the other one won't be diagonal if you chose the total angular momentum basis. And so you kind of have to make a judgment call, and usually the judgment call is, which of them is most important? Is this the big term, and this one's a little term, or is this the big term and this one's a little term? Sometimes that's not necessarily the best thing. Sometimes the judgment call is just which one is going to make the arithmetic the easiest, and that comes from experience to some extent. Okay, but just to emphasize the ubiquity of this trick, more generally, it's not just a feature of spin. So more generally, if I have J1 dot J2, I should think immediately, what happens if I write that as 1/2 J squared minus J1 squared minus J2 squared? Okay, and that is a sign that you should choose a basis, which is the total angular momentum basis that corresponds to the complete set of commuting observables, J squared, J1 squared, J2 squared. Okay, and that's the total angular momentum basis, because then those things are just diagonal. Okay, and the J's that will occur are going to be the following. If you take J1 tensor product J2, the resulting direct sum, the total angular momentum eigenvalues, the biggest one that there can possibly be is J1 plus J2. Okay, the next biggest one is one less than that. And so if you take this direct product, you get the direct sum of all of these things down to the lowest possible value, which is J1 minus J2 in absolute value, because it can't be negative. Okay, and so this is telling you what are all the possible total J's that can occur in the total angular momentum basis. Okay, and we will see more of this in the next set of lectures. Okay, questions on any of this? All right, so let's do a classic example as an application of this to actual physics. And this application is the hyperfine splitting of the hydrogen atom. Okay, so to tell you what the hyperfine splitting does, I'm just going to write down the Hamiltonian with a little HF for hyperfine. And it turns out to be a constant. I'm going to call the constant A times the dot product of the electron spin in the hydrogen atom with the proton spin in the hydrogen atom. Okay, that's all it is. And experimentally, the constant A happens to be positive, which is an important fact. So from everything I've told you, there's no way that you would know necessarily that that was true, but I'm telling you it is true. If you take the next semester of quantum mechanics, we will derive what the constant A is. And so we'll be able to prove it's positive, and we'll be able to evaluate it really as a number. But for now, it's just some number. And so the interpretation of this, though, is the proton, in addition to producing an electric field, produces a magnetic field. Along its spin direction. Because what other direction would it point in? There is no other special direction associated with the proton. And then that magnetic field acts on the electron spin, which is S sub E. And the Hamiltonian has to be a scalar quantity, so I can't take the cross product. And so the only thing it could possibly be is the dot product of those two spins. And then you just have to figure out what the number A is. Okay, so let's figure out what this Hamiltonian does to the states of the hydrogen atom that we've already considered. So first of all, we want to have a labeling scheme for them. The states of the hydrogen atom we can label in the following way. There's the principal quantum number, the orbital angular momentum, and the z component of it, which we were calling it m, but now we're calling it m sub l, because there's also the spin and its m value, and there's the proton spin and its m value. Right, so there's a big complete set of commuting observables, and those are the eigenvalues. These for the electron spin, these for the proton spin, and the first three are for the spatial degrees of freedom, the actual, classically, the actual motion of the hydrogen atom electron. Okay, and so this is a product basis. It's a product basis because the individual m's are all listed there. But we know that we could also write a state, a complete set of states that are an ortho basis by instead taking total spin for each of the electron and proton and the total spin by adding them together as total, and then the z component of that. So they're calling that m of s total. Okay, and that's the total spin basis. Okay, and from what I told you, when you see this dot product of angular momenta, that's a good indication that we want to use the total spin basis. So let's see how that works. Okay, what's our total Hamiltonian? It's the orbital part, which we've already solved, plus this hyperfine part. Now, it turns out there's also a fine structure part of the Hamiltonian and something else called the Lamb shift. But what I'm telling you is those don't actually make an impact on the ground state, which is all we're going to worry about today. So I'm just going to write them as plus dot dot dot. And I'm just going to say that they can be ignored. Okay, and then the good thing about the orbital part that we solved for the hydrogen atom and this hyperfine part is they just completely commute with each other. And so they have simultaneous eigenvalues. And eigenvectors. Okay, and so we can just compute this hyperfine Hamiltonian as if the orbital thing was just a fixed number. When you have commuting operators, it's just as if they're fixed numbers with respect to each other rather than operators. Okay, and then the other thing that we said we should do is when we see a dot product of this, we should use this trick here of rewriting it. So let's go ahead and do that. So the hyperfine Hamiltonian is our constant divided by 2 times the total spin squared minus the electron spin squared minus the proton spin squared. Okay, and the electron spin squared and the proton spin squared are just numbers because they're fixed. They never change. There is, in fact, no way to change them. Okay, and s squared is not fixed, but we know what its eigenvalues are because we computed the addition of 2 angular momenta. So it has eigenvalues 2h bar squared, 2h bar squared, 2h bar squared, and 0. That's what we worked out. And this is m sub spin total equals 1, 0, and minus 1, are those triplet states. Okay, and so right away we know the eigenvalues of the hyperfine Hamiltonian. We just plug in those numbers. One of them is the constant over 2 times 2h bar squared minus 3h bar squared over 2, which is positive constant h bar squared over 4. And those are the eigenvalues for the triplet states, the spin 1 states. And the other one is a over 2, and now I plug in 0. Okay, and those therefore come out to be negative 3a h bar squared over 4, and that's for the singlet states. Okay, and so each state that we had before, and by that I mean if you paid attention only to these eigenvalues, each of these eigenvalue states is going to get split apart depending on the spins. And we've just worked out how they get split apart. Okay, and so each state gets slightly split. Okay, and so if I, for example, consider the ground state with n equals 1, naively, up till what we had done so far, there was just one state there, but now the triplet is going to be slightly higher, and so there are 3 states up here that are still degenerate. The triplet states with ms total is 1, 0, and minus 1, and then there's the singlet state, which goes down by 3 times as much. Okay, and so that's ms equals 0. And so now one can have transitions completely different from the Lyman and Balmer and other transitions that we talked about before, between, not between different ends, but just in the ground state between the upper triplet set of states and the lower triplet set of states. And so you can have light from the transition. Okay, and to work out what the light energy is, it's delta E equals a h bar squared. There I'm just taking the difference between these things. Okay, and there's where you need to know what the number A is. And so if you plug in what the number A is, it turns out to be, this is 5.87 times 10 to the minus 6 electron volts. And that's going to be h bar omega for your photon that gets emitted or absorbed in this transition. That corresponds to a frequency of 1.420 megahertz. Okay, and this is a wavelength that turns out to be 21.4 centimeters. So it's a macroscopic wavelength. And this is coming from, this is a signal of atomic hydrogen. It's the transition between the ground states of atomic hydrogen. Okay, so it turns out this transition is very highly suppressed. It doesn't happen very easily. But if you consider the fact that outer space is very big and mostly empty, and there's not, in lots of outer space, there's not much else to look at, then even though this is a suppressed transition, you're still going to see it happen. And in fact, this is a way of mapping out in astrophysics and cosmology the atomic hydrogen throughout the universe. So this is an extremely important, this is called the 21 centimeter line from hydrogen. And now we've understood where it comes from as transitions between the no longer degenerate components of the n equals 1 ground state of the hydrogen atom. Okay, so that's a nice example. We will do examples of other addition of angular momentum next time, which I guess is a week from today. Okay, and so I have an announcement to make regarding the final homework and the final exam in this course. And that announcement is that I've decided, because of all the COVID disasters, and they keep sending us warnings that this might happen anyway beyond our control, that we wouldn't be able to have a final. So I've just decided to cancel it. We won't have a final instead, and we won't have a last homework set because it's too hard to squeeze it in. So instead, your final, I'll send an email with this information and more information about it. Your final exam will be a long homework set type thing. So it will be take home. Okay, and then the rules about when it will be due. It will be due either, I have to figure out when I have to have my grades turned in, but it will be due either the 10th or the 11th. Of December. I'll make it the 11th if I possibly can to give you more time, but I have to figure out when my grades have to be turned in, and they haven't actually told us that yet. Okay, so I hate to do that because I like having the year end with a nice exam where we can all prove what we learned. But on the other hand, this is a really bad year, so we're just going to skip. All right, any questions on the exam situation or the lack of final exam situation or this lecture?
I got a question on the content.
Okay.
Okay.
On the content of what?
What you went over today.
Good, okay.
Okay, so on page 150.
Okay.
Equation 924. So basically, okay, here's my question is,
So that's
how did you come up with those vectors? I'm still lost on it.
It's a definition. So just to let other people know what we're talking about, we wrote down that this is represented by 1, 0, 0, 0, and up arrow, down arrow is represented by 0, 1, 0, 0, and down arrow, up arrow is represented by 0, 0, 1, 0. Okay, and similarly like that. And so all we're doing is we're saying whenever we have a representation, we take our orthobasis kets. In this case, there are 4 of them. There they are. And we associate them with the unit vectors for the matrix representation. And we need to choose the order so that we're very specific about it. And so that's what we've done here. 1, 0, 0, 0, 0, 1, 0, 0. Okay, so this is what we always do in a matrix representation. We choose our orthobasis kets, and we associate them with these column vectors.
So it's not that you took like one of the, for example, spin up, the half spin up state.
No, we did not do any sort of calculation to do this. This is a definition.
Oh, okay. So because I was thinking maybe you put these vectors on top of one another. I was kind of confused by that. So that's not what you did.
Not at all. No.
Okay. Yeah, I'll let other students ask before I go on. Does anyone else have any questions? Okay, well, I'll ask them. So Professor